You know, back in 2014, a single research paper dropped an idea so elegant and powerful, it completely changed the face of artificial intelligence. It was basically a blueprint for teaching a machine not just to recognize things, but to actually create them from scratch. That paper was called Generative Adversarial Networks, and it laid out a plan that would change, well, just about everything. So let's get into it. So think about it. For years, the big challenge for AI researchers was this. How do you get a machine, a thing of pure logic, to generate something totally new and original? How do you teach it to draw a face it's never seen before, or a number that's never been written? And the answer, as it turns out, was surprisingly dramatic. You don't teach it to be an artist. No, you teach it to be a forger. The whole genius of this paper is the idea that the best way to create something realistic is to get really, really good at faking it. And yep, this is the paper that laid it all out. Generative Adversarial Networks, or GANs for short. The idea was to build a system where two AIs, two neural networks, are basically forced to compete against each other in this constant, high-stakes game of cat and mouse. Okay, so to really get how this works, you gotta meet the two opponents. The paper calls them the generator and the discriminator, but let's be real, we're gonna call them by their true roles, the forger and the detective. This slide just breaks down the competition perfectly. On one side, you've got the generator, our forger. Its goal is simple: make fakes that look real. It takes random noise and spits out a counterfeit. And on the other side, you've got the discriminator, the detective. Its job to spot those fakes. It looks at both real stuff and the fakes and just gives a probability. Is this real or not? They are perfect enemies. Let's look a little closer at the generator. I love this because the paper itself uses this exact analogy. Just think of it like a team of counterfeiters. It starts with nothing, just digital static, and its entire mission is to turn that noise into something that looks like, say, a real dollar bill, or in this case, a real photograph. And then, of course, you've got the discriminator. It's the police force. It gets shown a whole mix of stuff. Some are genuine articles from a training data set, and some are the fakes from the generator. And its task is dead simple. Look at each one and shout real or fake. And every single time it gets one right, it gets a little bit smarter. All right, so you've got a forger and a detective. How in the world does this rivalry actually lead to something creative? Well, it's all in the rules of the game, the training process that forces both of them to become absolute masters of their craft. And this is where the magic really happens, the training loop. First, the forger makes a fake. Then the detective judges it. But here's the crucial part, the feedback. The system tells both of them the result. So the detective learns what to look for next time, but the forger also learns how it got caught. That feedback process is something called backpropagation. It's like a coach giving notes after every single play. They're locked in this cycle, constantly forcing each other to get better and better. The paper calls this a Minimax two-player game. It's a technical term, but it basically just means it's a game where one player's gain is the other's loss. The generator is trying to minimize the chance of getting caught, while the discriminator is trying to maximize its ability to catch fakes. It's a perfect mathematical tug-of-war. So what's the end game here? When does it all stop? Well, the goal is to reach this point called equilibrium. This is when the generator's fakes become so indistinguishable from the real thing that the discriminator is just completely stumped. It's basically just guessing, flipping a coin. It's only right about half the time. And at that point, you know the forger has become a master artist. Okay, so this all sounds amazing in theory, right? But what does it actually produce? Let's take a look at the payoff and see how this whole process builds something from total chaos into something incredibly coherent. When the game first starts, the generator is, well, it's awful. It has no idea what a face or a number is supposed to look like, so its first attempts are just what you'd expect, staticky, meaningless junk. The detective has a super easy job at this stage. But round after round, iteration after iteration, the generator learns from every single one of its failures. It's constantly being guided by that ever smarter discriminator, and it slowly starts to figure things out. And the results? They're genuinely stunning. And here they are, the actual results from the original 2014 paper. The AI learned to generate handwritten numbers that look totally real. It learned to generate human faces that don't belong to any living person. It could even create these tiny, coherent images of things like frogs and airplanes. And you have to remember, every single one of these images started out as pure, random static. Now, this is the most important question you have to ask about a model like this. Is it truly creating something, or is it just a really sophisticated plagiarist, finding the closest real image in its memory and just copying it? And the answer is a definitive no. The paper proves that these are brand new creations. The generator isn't memorizing specific faces. It's learning the abstract rules, the Platonic ideal, you could say, of what makes a face a face. It's learning about the typical distance between eyes, the structure of a nose, the shape of a chin. It's literally learning the grammar of an image. So the big question is, why was this such a massive deal? I mean, GANs didn't just produce some neat pictures. They fundamentally solved problems that had been holding back generative AI for years. Before GANs, generative models had some serious issues, and this slide just captures that leap forward perfectly. You can see older methods were slow and complicated. GANs used that fast backpropagation we talked about. Older models often made blurry, fuzzy outputs. GANs could produce incredibly sharp images. This was just a huge improvement in both how fast you could train them and the quality of the final result. And what's really cool is the authors saw this potential right from the get-go. They predicted this whole framework could be used for all sorts of things, from making images based on text descriptions to improving AI with way less data. And wow, were they right. This 2014 paper is the direct ancestor of the AI art generators and, yes, the hyper-realistic deepfakes that we see all over the place today. It really did unlock a whole new era. And all of this brings us to one last big thought. The goal of the paper was to create a forger so perfect it could replicate reality. And the incredible success of that project leaves us with a really profound question. In a world where machines can generate flawless fakes, how do we ever know what's real anymore?